Bismillahirrahmanirrahim. Assalamu alaikum. The recent solar storm in May 2024 was the strongest to reach Earth in 2 decades, and possibly one of the most spectacular displays of auroras on record in the past 500 years. In today's episode, we will have discussion with our experts on the recent G5 scale geomagnetic storm, space weather, and Earth's magnetic field. We have invited guests who have tremendous experience on this topic. I would like to welcome Professor Babatunde Rabiu, Director of UN African Regional Center for Space Science and Technology, Nigeria, Mr. Ayaz, Ameen, Director of Space and Atmospheric Sciences, SUPARCO, Pakistan, and Ms. Muneeza Ali, Manager, Geomagnetic Research, SUPARCO, Pakistan, and currently studying from Rhodes University, South African National Space Agency, SANSA. Thank you for joining us today. Before we begin our discussion, on solar storms, Professor Ayaz, can you explain the audience about the concept of Earth's magnetic field, how it protects us from space weather, and how useful it is for Earth habitats?
Okay, thank you very much, Ms. Adab. The magnetic field of Earth has basically two components. One is called intrinsic and the other is called extrinsic. The intrinsic part is by default originating from the sun, from the Earth, and because of more iron in the core, the dynamo process takes place, and we say that since the Earth is rotating, that dynamo is rotating, so we have an intrinsic magnetic field. The extrinsic magnetic field comes from the sun, because sun itself is a star which is propagating solar wind. In that wind, there comes charged particles, energy, and magnetic field along plasma. So when that hits Earth, there is a shield called magnetosphere, and that protects us from the outside magnetic field. Even then, the field enters, and consequently, one net field is observed on the Earth. So at a given location, we can determine the magnetic field of Earth, and we say that this is the value of magnetic field of Earth, say in nanotesla as a unit, and measure it. So the magnetosphere is basically the shielding for the Earth's magnetic field with respect to the solar wind, against the solar wind. So overall speaking, the magnetic field of Earth, or the geomagnetic field, is friend as well as foe at times, because when the extrinsic factors are increasing, then we have protection or consequences, and this interaction is actually known as space weather, because it starts from the sun and it comes to the Earth. So we are living in the environment, if you see in my background also, we are living in an environment, the space environment, which is vulnerable as well as useful. Thank you.
Thank you for explaining these concepts. I think Professor Babatunde, if you can now give us a brief overview of what solar storms are and how they impact Earth's magnetic field and space weather.
Well, thank you very much. The solar storms, or generally we use the word storms, they originate from the sun. The sun is very dynamic and it emits radiation in all directions. But at some occasions, some of the radiations are capable of reaching the head. And in that case, we say that the radiations are geoeffective, that is, they can affect the head. So these radiations are high energetic particles of the order of 10 raised to power 5 kilometer per second. And they come towards the Earth, as explained by Professor Ayaz. They interact with the magnetosphere, which is the layer of the magnetic field, which is highly, I mean, the magnetic field there is dominant. Magnetic field of the Earth is very dominant in that region. So they interact with this magnetosphere, and it's as a result of that interaction, the end point of that reaction really is that we have a kind of reconnection process, and this affects the geomagnetic field of the Earth, and is actually captured effectively in the geomagnetic field measurements, both using magnetometers and some other instruments with which we monitor the Earth's upper atmosphere. The storms, when they come, they cause it's a disruption, really. It's a disruption of the Earth's upper atmosphere, and it's very disruptive. Like I said, it affects, you can monitor it using the equipment, different kind of equipment, and it can also lead to depletion of the total electron content at times, and at times you have a kind of enhancement. So you have positive storms, you have negative storms. At the process, when the geomagnetic storms take place, there is an introduction of extra energetic particles into the Earth's magnetic field. And this also has implication because just like when you introduce particles into a particular medium, it will affect the refractivity of the ionosphere. It will affect the concentration of the medium. And that is why you can have the dragging of satellites. And some satellites may not be able to move at their usual speed. And this has implications on space-dependent technologies on Earth, and some other procedures that depends on space technology. I don't know if I should go further or I should pause here.
It's very, you have briefly explained us, and I think it will give the audience a foundation about the understanding of solar storms. Thank you, Professor. Muneeza, my next question is for you. If you can tell us the different types of solar storms, how do they vary in terms of their impact on Earth's technology and infrastructure?
Thank you very much, Sarab. If you look at the different types of storms that are coming from the sun, there are actually two main kinds. One of them is a radiation storm, and the other is a particle storm. And usually, what happens is most of the times when there is a solar flare, a coronal mass ejection or magnetic plasma ejection is usually accompanied with it, and it's on its way to Earth. If it's geoeffective, it's in the line of the Earth, and it's supposed to come in a few hours or a few days. So before that, we usually get a particle storm, like a very good influx of particles coming in, like it's been previously told. We have already discussed about this, but the thing is, the radiation storm usually travels with near speed of light. So what's the first thing that happens after a solar flare, or like a very powerful flare that just happened on the May 8th and 9th, and there was a series of flares, X flares. So it ionized the ionosphere to such an extent that there were long duration blackouts. I mean, the ionosphere was so energized that high frequency communication was not possible for many hours. It took many hours for the ionosphere to restore to its current state. Now, when we talk about the geomagnetic storms and the storm which accompanied the May 11th G5 category storm. So as was already mentioned, that the satellites which are in orbit, those are very critical infrastructure. Lots of investment has been made into putting those satellites up there, so they are at a very vulnerable position. And but what about the ground infrastructure? All the infrastructure near the poles, like in the higher latitudes. And when we talk about higher latitudes, we're talking about greater than 40 or 50 degrees geographic latitude, north or south. So all of these places consist of power grids and pipelines or any internet cables which are going under the sea. So those kinds of infrastructures are very vulnerable due to the impact of these storms. South Africa, or the South African National Space Agency, actually issued a warning for communication systems in the space and on the ground, and for the power grids which are functional for providing or supporting the national grid. So they had to give an emergency alert for them to be on standby. If necessary, they should shut down the grid for some time. But the National Space Agency is actually in coordination with the stakeholders. They're conducting a study about how much the impact has been made. So in order to better manage any critical damage which happens, because now these storms are going to be frequent visitors. Now that we are entering the solar maximum, one of such storm has already arrived, and we still have that same region which produced such storms. It has rotated back into view, and it's still on the sun, and it's still giving out those radiations and particles and X flares. So it's not like a very critical emergency, but it only happens when these sunspot regions are on the Earth view, and the higher latitudes, which have more critical and vulnerable infrastructure, they have to make mitigation measures. Thank you.
Okay, we have described this. Another question, if you can also answer that, how these geomagnetic storms are monitored and forecasted. Professor Babatunde also told us that there are certain instruments. If you can briefly describe about those instruments.
Yes, surely. For geomagnetic storm monitoring, I can quickly answer this, because we need a certain set of instruments like magnetometers, which measures the magnetic field on the Earth, the ionosonde, which measures the radio blackout absorption in the ionosphere, or any kind of ionospheric conditions, be it plasma bubbles or drifts of particles or winds. So it's like two main critical instruments are these. Apart from that, we can have a very low frequency receiver, which can see what the solar flare in just near real time. Apart from that, we have another instrument known as a solar radio burst monitor, which can track the CNE on the ground while it has already entered the interplanetary medium. And from that, we can see how fast or how slow it is traveling. We can calculate the drift speed of that. So we have these an array of instruments which can track the storm from the sun. Once it has ejected from the sun and it has entered the medium of travel from the sun to any part of the interplanetary medium. And we have, it's just not instruments. Sometimes there are models which can input all of these data coming in from the instruments, and it can forecast the arrival of these plasmas, of these velocities with which the particles are traveling. So one of the model is NLIL model, and that model is run by two regional warning centers. One of them is the Space Weather Prediction Center, and the other one is from the UK Met Office, Moswak. So both of them have their own versions, and they run these models in real time and find out the possible time period of these magnetic storms in order to reach us. When it was for the May 11th magnetic storm, it's the accuracy. I'm telling you about the instruments and the data which was inputted in the model. It was so accurate that we were able to find out that the storm had arrived in just about plus minus 15 minutes of variation. So even the Space Weather Warning Center at SANSA was able to find out with a good confidence of just half an hour. We were able to find out that the storms can arrive in a time confidence of plus minus 30 minutes. And it was a very good estimate.
Thank you, Muneeza, and also thank you for sharing your experience at SANSA. If I can request Professor Babatunde and Mr. Ayaz, if you both can also share the international practices being followed in Nigeria and Pakistan for monitoring the solar storms. Geomagnetic.
Well, I think I would just like to go first here so that probably you can also excuse me after this moment.
Yes, please.
Okay, thank you very much. Yes, in Nigeria, we have various equipments. We have optical facilities with which we monitor the upper atmosphere. We have an interferometer. We have an Earth-sky imager. We get involved in a lot of international cooperation, and we also work with the national groups and scientists. We have a close relationship with SANSA, and like mentioned by Muneeza, one of the models that is also being used in SANSA, also done in partnership with our scientists, and we have a lot of movements between the Nigerian scientists and SANSA scientists as well. So we have magnetometers. We have different kinds of equipments, the GPS, GNSS receivers, radar systems, and that we're using to monitor the equipments, and they take real-time measurements. And also we operate space weather nowcasting systems, as well as forecasting up to 3 days. And we have a model in place that can also monitor, that you can use to study the space environment for a long time, that has been published and are still being used. Like I said, some components are being used. They were developed together with some scientists from SANSA. So we have an operational systems for monitoring space weather, and we've been sharing this as well with some other nationals within Africa or outside Africa. Right now, I'm with the Institute for Atmospheric Physics or Research in Germany, also for a collaborative purpose. The space weather monitoring is actually universal nowadays, and it's quite interesting, really, that there are a lot of developments based on emerging technologies, and international cooperation is very, very effective and is the best approach to space weather monitoring. And it has been coordinated universally. Next week, we'll have a United Nations workshop on international space weather here in Germany. And from where I am, I will be attending that program by weekend. I will be over there. And we hope to continue with our deliberation on space weather monitoring. And it's quite effective. Thank you very much. And thank you for having me here. Please, I will seek for your permission to join my host here to take me to the office. Thank you very much.
Thank you so much, Professor, for joining us. And thank you for explaining us and giving us a detailed answer of this question. Thank you. Sir, if you may please continue.
Yes. Thank you, Babatunde. It was really nice to have you.
Thank you.
Thank you.
As the professor mentioned, this is a universal phenomenon now. So according to United Nations Committee on Peaceful Uses of Outer Space, every point on Earth has its own importance. So when we are monitoring space weather, we are doing a collective science. We have instruments in Pakistan, the similar kind of instruments as Professor has already mentioned or Muneeza has mentioned previously. So they include ionosondes, magnetometers, variometers, total content monitors or receivers, solar radio burst receivers, sudden ionospheric disturbance monitors, and other equipment. So with that network spread all over the country, we gather the data from those remote data acquisition sites to this place I'm talking from. This is Pakistan Space Weather Center. And after collecting the near real-time data, we process the data here, and then we disseminate the information to our users. So we have a nowcast kind of system, and that system includes generation of daily space weather summary, which gives you the overview of the space weather, ionospheric conditions, geomagnetic field variation conditions, and the latest solar images processed locally in order to show that which regions are active and which are more likely to emit any emissions, just like coronal mass ejections or flare. So in this process, we have reached to a point where we can say that we have reached from research to operation part. Previously, there was a lot of research all over the world, and now collectively we have become able that we are now propagating or disseminating the information for users in order to mitigate the effect of the space weather. So with this, there are certain models, as Professor also mentioned, and Muneeza has previously said. The global models are International Reference Ionosphere, which is an ISO certified model, which gives the snapshot of ionosphere. And for geomagnetic field variation, there is IGRF, International Geomagnetic Reference Field Model. So both models are updated with the help of data from all over the world, including Pakistan. And every 5 years, they have new versions of these models, the upgraded ones. Now, in addition to that, every regional warning center or a space weather monitoring center develops its own regional model. So we are also working on those models with the help of machine learning and artificial intelligence tools also. So previously we had a publication over equatorial ionization anomaly region, where we use the retrospective data in order to develop a model to forecast critical plasma frequencies in the ionosphere. And the confidence of that model was greater than the international reference ionosphere model, which is a global model. Usually regional models behave better than the global model. So we are also equipped with the similar kind of instruments, and the science cannot be done in isolation. So it's a collective effort, and everybody is contributing, everybody is taking advantage from someone else's observations and experiences.
Thank you so much, and thank you for educating us about these international practices. Another question, Mr. Ayaz, that I have is that we know about the recent solar storm, but other than that, are there any notable historical solar storm events that have had a significant impact on Earth's technology or atmosphere?
Yeah, there was one event which is mentioned as Carrington event. I think, if I'm not wrong, 1849 it was, and that happened in an era when there was not much technological advancement occurring in the world, but the only technological asset was telegraph, and that telegraphic system collapsed. It burned out due to GIC, which is geomagnetic induced current, the current induced in the ground, and it went to the cable, and everything was blown off. And the magnificent view of aurora, usually they are seen over poles, near north or south poles, and there is a region which is called auroral oval. So you can see the aurora in that auroral oval region. But during Carrington effect, the aurora were seen up to the latitude of New Delhi, which is almost equivalent to Islamabad, Multan. So they were quite low in latitude observed at that time. In modern days, if we talk about such a storm, there was a Halloween storm which occurred in 2003 on 31st of October. But recently, the storm of 10th or 12th May was also of G5 intensity, and that was, it is estimated that it was severe than even the Halloween one. Because in this storm, Hermanus also observed the aurora in our region. We could not see that, but in neighboring countries, there were auroras seen at the similar latitude of our capital city. So that was also an intense one. This recent geomagnetic storm of G5 category is being treated as one of the top 5. And for the correction of record, I would mention that we have 3 types of storms. Basically, one is called radio blackout, when there is a flare and the HF frequencies are curtailed. Second one is called the solar storm because of the solar energetic particles, and the third one is called geomagnetic storm. So collectively, we call them space storms, and they have certain timelines. So if there is a flare, that reaches to us in 8 minutes 20 seconds with the speed of light. Then if there are energetic particles, they travel and they reach us, say, from 30 minutes to up to 2 days. And if there is solar wind disturbance in terms of magnetic field, that takes 2 to 3 days to reach us. So this flare, there is CME, there are energetic particles, so they have different timelines. And what is bringing those things to us is the solar wind. And that fluctuation in solar wind at times is very large, because average speed of solar wind, we say that it is 400 or 450 kilometers per second. And at the time of storms, it can reach up to 1,000 kilometers per second. So more than 2.5 times. So this is how it works. And as I already said, we are living in such vulnerable environment because of the sun.
Thank you so much, Mr. Ayaz. Muneeza, since you are in South Africa, and since you have also witnessed the aurora, the recent aurora. So if you can explain the science behind this and how solar storms contribute to their formation.
Yeah, thank you for that. Yes, because let me begin with the background that I used, and you can also see this was the aurora that we witnessed just a few kilometers from this town that I'm staying in. This place was known as Hanskai, and people there, it was a clear sky, clear night. And because Hermanus was cloudy, we kind of missed it. And the cloud had an overcast, we couldn't see it all the way through. But this town, it was just like 10 or 15 kilometers away from Hermanus, and they captured this red auroras. So the reason why these auroras are red is because that because the ionized particles, because they are so energetic, they've already hit the poles. They still have some energy to travel all the way down to the lower latitudes, at least the mid latitudes, and they ionize the oxygen in the altitude of 200 to 500 kilometers, very high up in the ionosphere. And this is the reason why they emit photons when they interact with the energetic particles up there. They emit these red emissions, red photons. So basically what happens is that when a very energetic magnetic storm happens, these energetic particles have a tendency to follow the magnetic field lines. They always travel along the magnetic field lines, and once they enter the Earth's magnetic field, all the magnetic fields coincide at the poles. For the Earth, the magnetic fields coincide at the poles, the North and the South Pole. So all those magnetic fields they give like a channel for all these energetic particles to travel all the way down. And when you see the auroras at the poles, they are of different colors. They emit different radiations because those energetic particles interact with different gaseous states. Sometimes they interact with nitrogen, most of the times they interact with other trace elements. So when you see purple or green auroras, they are actually nitrogen emissions at different altitudes. And the green emission is from the nitrogen excitation, which happens at a lower altitude. And when you have those red auroras, they are oxygen atoms which emit those photons at a little higher altitude. Sorry. So this is actually what happens. And there are actually names for those auroras. The auroras which are seen in the northern hemisphere, they're known as aurora borealis. And the auroras which are seen in the southern hemisphere, like the one in Australia and South Africa, they are known as aurora australis. I will tell you one more interesting thing. The last time the auroras was seen in the South Pole, in the southern hemisphere, was way back in 1989. And that was when the auroras were so intense, it actually lit up the atmosphere around the biggest city, one of the biggest cities known as Durban, and thousands and hundreds of thousands of people witnessed those auroras in 1989 when there was an energetic magnetic storm. So, what I'm trying to say is auroras are actually very more common in the northern hemisphere, but in a G5 category for a very energetic geomagnetic storm, these auroras can be seen in the southern hemisphere as well.
Very interesting. So on a concluding note, I would like to ask both of you how we can raise public awareness about the risks associated with solar storms and the importance of space weather forecasting. Mr. Ayaz, if you may please start first.
Thank you. Very interesting question. And as Muneeza told about aurora, I would pick from a note. Actually, the public is already interested, as I say, that seeing is believing. So since the beginning of our human race on this earth, I think aurora observations are one of the first observations which were made by humans. And that's why they started worshipping these lights also. So every time we saw such phenomena, we started worshipping it. I mean, this is the human history. And after getting to know the science, then we started some analytical thinking and our intellect was improved. Now in today's modern world, you cannot say that ignorance is blessing. Ignorance is no more blessing, because if we just talk about this space weather, if we don't know about it and we are ignorant, we can go back to Stone Age after one big storm. Why? The reason is every technological asset is vulnerable, whether it's in space or on ground. So if there is one big flare or one such event like Carrington, we can go back to 1950s when there was no satellite and nothing. So regarding the awareness among public, that is the responsibility of all of us. And when we are scrolling the mobile screens or browsing through the internet, we are just getting the information without processing it. So in order to process that information so that information becomes knowledge, we need to start from the ground level, that is, say, from our schools. And then after every progress in their grades, I'm talking about Pakistani education system, we need to inculcate this thinking and this knowledge to students. Our responsibility, how are we contributing in it recently in this geomagnetic, on this geomagnetic storm of 12th May, we had telecasted, in fact, a press release, and public was made aware. Then we have a space education awareness drive managed by SUPARCO that is contributing at school levels and creating public awareness by transferring knowledge and sharing experiences. So we arrange such events also. Additionally, we have websites, we have other sources. So whenever we are together amongst our friends or family, we talk the basic science or the phenomena which are, or the science which is governing these phenomena. So we take the responsibility and we can share our knowledge and experience with general public. So I take this responsibility that when I'm with my family and friends, I explain them in layman's language that what is actually happening, what is the science of aurora, what is the science behind geomagnetic storm. So this way we can pass on the knowledge.
It's truly commendable about the efforts you are taking individually as well as on an organization level. Thank you, Mr. Ayaz. Muneeza, if you may add further. Your mic
Muneeza, you're on mute.
Apologies for that. Thank you, Sadaf. Yes, I would like to add something along the lines which already Mr. Ayaz has talked about. Since I'm also from the same organization, I know the measures that we collectively take. But when I'm here in South Africa, I see that similar or very similar measures have already been taken. SANSA also has a science engagement which pretty much delivers the same kind of goals and outputs like the SUPARCO's Space Education Awareness Drive. They go to visit remote cities, remote places, and they try to educate. They target the young children, you see, because the young minds are fresh to cultivate. They are more adaptable, they're more flexible. And when they have captured the attention of those young minds, they talk very excitedly back in their homes and their families, and then that's how they seek to spread awareness. Because when the parents are interested, they contact SANSA and they ask for a visit, which SANSA openly invites, and they have a open day every week on Wednesday. So in the afternoons on Wednesday are always dedicated to such visits from the families, from the parents of the children who have already been visited by these officials. Moreover, they are also making use of their local languages. I think there are about like 12 languages which are recognized and which are spoken in South Africa. And the most common are the three. Well, one of them is Afrikaans, the other one is isiXhosa, and the third one is isiZulu. So they target these languages. They try to hand out such pamphlets and colorful cartoons and colorful posters in the handout material in these languages so that it is able to reach those audiences who can understand and speak these languages. I want to show you one of the pamphlets that is available for everyone. I hope you can see it. It was already published in back in 2016. So they talk about the space weather impacts on aviation. Then they have another pamphlet on economic impact of space weather, and it's along the lines of the policies which are in practice. They are all open to the public. The third one is the safety security applications from a magnetically clean environment. Because Hermanus Magnetic Observatory was established in 1939, all those years back, and this the mayors of the city who have been in positions of power, and they have taken decisions to maintain Hermanus as a magnetically clean facility. So what I mean by that is there are no railway stations They are around the enclosure. There are no parking areas. This area is secluded only for magnetic observation. We have a wide space where no further infrastructure is permitted to be developed, so that the magnetically clean integrity of this place is intact. And one of the major contributions that Hermanus Magnetic Observatory makes is for the DST, the Global DST Index, that's known as the Disturbance Storm Time Index. And the Disturbance Storm Time Index gives you a real-time measure of how severe a magnetic storm is. So when the magnetic storm was happening all over the world, who are scientists and researchers, they were looking at this DST index and they were watching it take the most deepest value. And I think the value which was calculated from this DST index was 412, minus 412 nanosecond. So that has been quite intense in a very long time. So these are some of the measures that SANSA takes on their level. On all the researchers, scientists, not only the Science Engagement Unit, but the researchers and scientists also, when they talk about these things with their families, they talk in layman's terms. They try to make it as simple as possible so that people who have no background whatsoever can understand at a very fundamental level. Thank you.
Yes, thank you so much for sharing the innovative practices followed in South Africa. I'm sure it must be beneficial for our audience as well. So, as we conclude this fascinating episode on solar storms, we extend our heartfelt thanks to our esteemed guests, Professor Babatunde, Mr. Ayaz, and Ms. Muneeza. Your insights have enriched our understanding of space weather, solar storms, and the profound impact on the planet. On this note, I would also like to thank our audience for joining us today. Until next time, stay curious, keep exploring. Goodbye for now, and Allah Hafiz.